Yang Li from National Taiwan University, and IBM talking about spectral truncation and rescale for model merging.
So hello everyone, I'm Yang Li, a second-year master's student from National Taiwan University. It's my pleasure to introduce our work, STAR, Spectral Truncation and Rescale for Model Merging. So this work was done during my internship at IBM Research last year. With support from National Taiwan University and Academia Sinica. So let's begin with some background of model merging. With the popularity of pre-trained large language models, the same architecture is often deployed to fine-tune individual NLP tasks. A natural question then arises about whether it is possible to merge this fine-tuned model back into one unified multitask model. And that's why model merging has become such a popular topic today. Since that one of the main goals of model merging is to reduce the computation burden, the merged model should be derived without further fine-tuning. This means typically here, the whole merging process can be conducted by CPU only. So despite there are several lines of research focused on merging models with different architectures, we only focus on the center setup here, where the models were fine-tuned with same architecture and from the same pre-trained initialization. Besides, several existing methods perform inference on the original test data during merging, such as feature merging and ADA merging. So in contrast, our paper focuses on the data-free scenario. We make no assumption on that data can be available during merge time. To get an understanding about what model merging will look like in real world, let's do a simple demo here. So first, we fine-tune a language model on GSM8K to get a math model with accuracy 90%. Same things go for MBPP and Alpaca to get a code model and a chat model. Then we perform certain merging algorithm on these three models, and finally evaluate the merged model performance on original tasks. So to decide how well the merging algorithm is, we will simply calculate the average normalized performance of the merged model. In this scenario, it would be 80.83. Now, an interesting point to note is that the average normalized performance of the merged model should be higher than that of the pre-trained. So for example, in this scenario, we go back to evaluate the pre-trained model on these three tasks and check that the merged model performance is indeed higher than the pre-trained. Okay. So an important work in model merging is task arithmetic, which is published in 2023. Task vectors were formally introduced and defined by the difference between parameters of the fine-tuned model and the pre-trained. Task vectors mark the updates made to the pre-trained weight and when fine-tuned on specific tasks. Then model merging is applied by this simple formula, with alpha being a tunable hyperparameter. So since then, model merging essentially studies ways of using different task vectors and then add them back to the pre-trained model. So for example, TIES, also a well-known method as task arithmetic. TIES proposes a three-step approach to fuse task vectors. A small note here is that despite the term vector, task updates are often considered in their matrix form, which is native from the language models. Some of the papers nowadays start to call this task matrix instead of task vectors. And I think that it is better because it causes less misunderstandings. After going through the basics of model merging, let's discuss three key challenges we identify and aim at solving in this paper. The first one is the cumbersome process of hyperparameter tuning, which we call it hyperparameter dependency. Since most of the merging methods involve one or multiple hyperparameters, users are required to tune them either with validation data or simply by trial and error. To give an example, here's the merging results reported by TIES in their paper. But if we look behind the scene, so go into their appendix, we can find that the optimal hyperparameter behind this figure is actually varies significantly. So depending on both the model combinations and the number of models being merged. So this is the first challenge we identified. The second challenge is the inevitable decrease in merge model performance as the number of models merged increases. And we referred it as task conflicts. As presented here, one can see that in some cases, especially when the number of models is large, task conflicts cause the merge model to perform even worse than the pre-trained model, so losing the entire purpose of model merging. Then the final challenge we identified is the limitation of specification approach. In specific, to address task conflicts, one line of work specifies task vectors, retaining only their dominant information. However, prior methods only specify task vectors in parameter space, which might fail to capture the most useful information. Take types for example again. The authors found that only a small fraction of high magnitude parameters in task vectors are responsible for the fine-tuned performance. Therefore, they propose to specify task vectors by trimming small magnitudes. Another example is model breadcrumb. We suggest that in order to mitigate task conflicts, both large outliers and small perturbations should be trimmed in task vectors. So those two works are both work in parameter space. This is the third challenge we identified. So after introducing the three challenges, let's see how we solve them. We introduce STAR, which again means spectral truncation and rescale. Our algorithm is pretty simple. We can summarize it with 4 key steps. For each task vector, we perform the first step, SVD, and second step, truncation, and finally the rescale. At the end, we simply average over all the truncated and rescaled task vectors to get the merged task vectors. Now, I will start by explaining the algorithm by explaining what motivates us to specify task vector in spectral space instead of parameter space. The main idea is quite straightforward, actually. We think that if the task vectors are in matrix forms, like we previously discussed about, we should somehow examine them using matrix properties. To formally compare specification in parameter space versus spectral space, we have conducted a toy experiment here. So we simulate a scenario of merging 10 models by fusing task vectors with 9 times random noise. We measure the extent of specification by Frobenius norm. And through the figure on the slide here, we can see that under sense specification budget, spectral space is better to extract useful and noise-resistant components compared to the parameter space. So here we are actually tackling the third challenge by proposing a new specification approach. Also, I would like to mention that the more rigorous proof is in our paper about the spectral truncation step. So here is just a toy experiment that motivates us to propose the spectral truncation. Next, let's talk about how to rescale. So the main idea is that we assume the spectral truncated matrix should be somehow rescaled back to its original sizes, kind of similar to the compensation operation in dropout. To be more specific, we perform rescale by retaining matrix nuclear norm. This means that for all the remaining singular values, we perform this formula shown on the slide now. So here we show an example of merging 4 T5 models. And one can see that rescale indeed help by boosting the final merge model performance compared to the no rescale. And again, a more rigorous proof about this step can be found in our paper. So please check it if you are interested in the mathematical part. So circle back again to our workflow. Let's finally explain about how to design the truncation extent in STAR. As the distribution of singular values varies both within and across task vectors, we introduce a hyperparameter eta here, so that the remaining ranks of each matrix is decided and controlled by it. So we would like to highlight that the design of eta allows truncating components adaptively, resulting in different ranks across not only tasks, but even layers. As in the figure in the below, by setting eta to 40%, the remaining ranks differ across layers in one fine-tuned model. So now if we recall, by introducing only one hyperparameter here, we are actually tackling the first challenge, which is the hyperparameter dependency. Next, we also perform sensitivity analysis for hyperparameter. We pick ties as a comparable, since ties also has a single hyperparameter called k, and it works very similar to eta in star, as they are all governing the extent of specification, but one in parameter space, one in spectral space. So the results here suggest that the performance of star is a bit lower hyperparameter sensitivity. What's more surprising to us is that the one-shot star performs even better than grid search ties. So note that this analysis here is also related again to tackling hyperparameter dependency issue. Okay, now let's finally see the final merging results with several baselines. We have two major findings here. The first is the average normalized performance decreases as the number of models increases as expected, but star's performance decay being the slowest. Second, star remains a strong model merging method across different architectures. We only show the performance of FLAN-T5 large here, but you can check our paper for FLAN-T5 base and Mishore 7 billion instruct. So these findings show that we have successfully mitigated the task conflicts we mentioned earlier. So for now, the three challenges are all resolved or mitigated. So to conclude what we have talked about today, we first discuss three main challenges in model merging. Then we propose to solve each of these challenges by star. In specific, first, we conclude we could break the limitation of specification approach by removing noisy components in spectral space. Second, we could mitigate hyperparameter dependency by introducing eta. So eta can do two things. First, they could automatically determine the remaining rank. And second, by experiment, we found that it won't have much influence on the merged model performance. And finally, our experiment results show that we have successfully tackled task conflicts, which is the main challenge we face in model merging. So model merging is actively developing. If you have any thoughts on our paper or any idea to build a new algorithm, please feel free to reach out or discuss with me. Besides, I will be applying PhD this year, so I would love to connect and discuss any potential cooperations or projects. Thank you for listening and welcome for any questions.
Thank you for the great talk. Any questions from the audience? Okay, maybe one question from myself. So if you go to your empirical results, it seems that for all the methods, including star, the performance would degrade, right, as you merge more and more model. So do you have any insights on that? Is that kind of inevitable, or can you further design more approach, maybe taking some information from the spectral space by comparing the task vectors that could mitigate this issue?
Yeah, I think at the end, this kind of decaying performance is inevitable because we are merging models without further fine-tuning. So initially, those directions are non-relevant to each other. And to further mitigate this decay, there are several methods proposed after our publication. So actually, there are several works about spectral truncation or SVD. That stuff is popping out already. So maybe we could discuss after the talks about that.
Okay, great. Thank you.
Thank you very much.